Hello everyone, this is the second problem we're going to handle in our small section where we talk about problem solving in projection of solids through the software SolidEdge. The problem we're dealing with now is of a cone with diameter 40 millimeters and an axis of 50 millimeters. It is resting on the ground on a point on its base circle in two different ways. One way, it makes an angle of 45 degrees, its axis rather makes an angle of 45 degrees to VP. The other, the top view of the axis makes an angle of 45 degrees to VP. And in both cases, the axis makes an angle of 30 degrees to HP. Since the object is resting on the HP and inclined to the HP, we are going to start from the top view. So that basically helps us assume that the axis is perpendicular to the HP so that we can see the true shape in the top view. Okay, so like every problem, we're going to start off by the object. Remember, the object itself and its boundaries will be 0.5 millimeters thick and a continuous line. So I mark the circle, I mark the dimension, which is going to be 40 millimeters. Okay, immediately after marking the dimension, I'm going to create the generators, the slant generators on cone. So to do that, all I need to do is split my circle into at least 8 different parts. Okay, I know you've been told to do it in 12 on a drawing sheet. 12 is essential. Here, any number is convenient. It's not really that difficult for you to do as many pieces as possible. So for the sake of brevity, I'm going to cut this into 8 pieces. So it's 4 is already done. You need to make sure these 8 pieces are actually identically sized. So make sure they're 45 degrees apart. And again, to save a bit of time, you can use the mirror, rotate, and the other commands when you split this into 8 pieces. Okay. Like I said in my first video, I'm going to save a bit of time by skipping nomenclature to the end of the video or somewhere in between when I create a few cuts in the edit. Okay, so your top view is going to be a circle. So your front view is going to be a triangle. So I start from where the axis is. I know that the axis is going to be 50 millimeters in size. I'm going to mark it as such. Then I'm going to mark all the other points like so. There you go. So what I'm going to get right now is the base. The base is going to be, and I'm going to mark it such that I split it at these critical points. You'll get to understand why that is when we get to the second stage. Okay, I know that the center line is going to be my axis at 50 millimeters. I'm going to mark the 50 millimeters, and I'm going to also mark this line as the axis itself, which is the axis chain link line or the dash dot line, which is 0.5 millimeters in thickness. Once that is done, I go back to the generators. But remember, we can only darken the end generators. We cannot darken the generators in the middle because this is a cone. It has no natural edges. It only has one continuous surfaces. So the lines in the middle are just lines that we have come up with for the sake of convenience and nothing else. So that's your first stage. So right now you've got all the nomenclature done. So we'll zoom in for a better idea. So like I said before, whenever we are starting a problem from the top view, we always name the points in the counterclockwise direction. So that in the front view, you have A, B, C, D, and E visible, with F, G, and H invisible. And you also have the bottom end of the axis, O, invisible, where the top end of the axis, which is part of the apex in a cone, is going to be visible. So this is your first stage. So remember, this problem has to be done in 4 stages because you have 2 conditions for inclination with the VP. Okay, so we're going to solve the first things, which is inclination of the HP. Inclination of the HP is at 30 degrees. So like I said earlier, we first mark or we first select the entirety of the sketch, the front view. Then we go to the move command, make sure copy is on. We move the solid from one place to the next, make sure we place it on the XY line so that we satisfy the condition of the object resting on the HP. Next, we rotate. We rotate it such a way that the point on which the object is resting, let's say it is the point E, that is going to be our center, and AE is going to be our axis. So we know that the axis is inclined at 30 degrees to the HP, meaning that the base is going to be inclined at 60 degrees to the HP. So this is what you get. Okay. Normally, you have to look at the amount of space available for you to solve the problem. So here it's not such a big deal. You have more than enough space to complete the third stage of the problem. Okay. So we go on further. So in order to draw the top view in the second stage, you need to identify whether the apex or the base is closer to the observer, who's going to be up here. Obviously, for the observer, the apex is going to be closer, meaning that the base is not going to be the one that is visible. Nonetheless, we're going to mark all the points of the base. So you have A, A1, you have B and H in the same line, but B2 have to mark them, remember, same vertical, whereas B and D are on the same horizontal. So there's D, and then E. We know that E is going to lie on the XY line there. Next, we have F and H in these points. Last thing, the point C and the point G, which lie on the same vertical line, like so. Sometimes you would get these prompts, which would result in an incorrect plot of the point. Make sure that doesn't happen, and always trim away the lines that you do not need. Okay. Last point that we need to mark is going to be the apex, which is O1 from there to there. So with all this marked, again, we're going to pause for a second so that we can get our nomenclature back in place. So right now you can clearly see that all the points in the top view of the second stage have been marked. So what I'm going to do now is zoom into the region we need and identify which is going to be visible and which is not going to be invisible. Obviously, as I said earlier, the base is not going to be visible. It's the apex that is closest to the observer that is going to be visible. So in order to do that means I skip darkening the base and I darken the boundaries. This would have been perfectly fine if this were a pyramid or prism, which would have natural edges and corners and the like. Unfortunately, in a cone, you have no natural edges, no corners, all of them would be perfect curves. So what I'm going to do is first draw the ellipse that is going to be the top view of this particular circle as a thin line. And then I'm going to draw the rest of the line. Okay, so ellipse is right near your circle. I'm going to use a command called ellipse by center point. So I select the center of the ellipse, select the end of the major axis, and the end of the minor axis. So that gives you your ellipse. Okay. Next thing, I need to darken the boundary. Then I'm going to draw a line from. I'm going to draw a thick line because this is going to be a generator. A line from O1 to. Remember, I am not going to draw the line to G, which would mean that the line O1G is going to intersect the base in more than one point, which cannot be physically possible. So I'm going to draw a line that is tangential to the ellipse that I've just drawn. And you can clearly see next to the cursor a line and a circle intersecting, showing that this is actually a tangential line. So once I've marked these two as tangential lines, I know that the left half of the ellipse here from the two tangential points is going to be visible because it's part of a boundary, and the right half of the ellipse is going to be invisible because it is going to come away, it is going to appear further away from the observer. So what I'm trying to say is if you just look at the front and top views of the second stage, you can clearly see that one half of the cone, so that's A, B, C, G, and H, is going to be closer to the observer compared to the other half, that is F, E, and D. So this is where we have to split the ellipse as a visible and invisible half. So what I'm going to do is use a command called split. The split command is near trim. So you have trim, trim corner, extend to next, and then you have the split command. So I select the split command, select the entity that I want to split. In this particular case, it's going to be my ellipse. Then to select the points at which I want the line to be cut into two pieces. So select one tangential point, select the other, which results in me having two different ellipses. One ellipse on the right, or rather one half of the ellipse on the right, the other half of the ellipse on the left. I know that the ellipse on the left is going to be the visible one, so I'm going to mark it as a thick continuous line, whereas the ellipse on the right is going to be invisible. So thick discontinuous line it is. And this is what my top view of the ellipse is going to, or rather top view of the cone is going to look like. One thing I've left out obviously is the axis, which we'll come to now. And again, the axis runs from the point O to the point O1. Unfortunately, we have a line from O1 to E, another from E to A. So what I'm going to do is split the line from A to E. So I go to the split command, select the line AE, and select the point O, which results in me splitting the line OE, or rather AE, into two pieces, AO and OE. The other thing is we've identified these as two different lines, which really will not work. So what I'm going to do is delete the line OE. This gives me a chance to show you another option called extend to next. Okay, so extend to next, as the name suggests, is going to extend a particular line till its next intersection. So I'm going to extend O1E till the point O. So it gets extended first till the line DF, then again till the point O. This would result in me getting one continuous line from O1 to O, which I can identify as my axis, which is a dash and a dot. So once this is complete, I get my second stage to be perfectly done. Okay. When we get to the third stage, this is going to be slightly different, because the third stage, I need to do two cases. One case where the axis appears to be at 45 degrees to VP, and the other case where the axis is actually at 45 degrees to VP. Normally in a drawing sheet, you would solve the problem in four different stages. But here, because we are working on a computer, we have the advantage of selecting everything, hitting Control and C together, so basically copying it, and pasting it on to another sheet. So what I'm going to do is solve the true inclination portion in one sheet and the apparent inclination portion in the other. So now I'm going to solve the first case where the axis is inclined at 30 degrees to HP, which we just did. Unfortunately, we forgot to mark it, so I'm just going to do that for a second. So that's the axis inclined at 30 degrees to HP. I now have to mark the axis at 45 degrees to VP. So the inclination to VP, remember, is seen here in the top view. Unfortunately, in the top view, we cannot see the true length of the axis. We know that the axis is 50 millimeters long, whereas if one measures the length of the top view of the axis, we see it is just 43.3 millimeters in size, which means that this is not the true length. So we can never ever apply true inclination to apparent length. So what we have to do now is find the apparent inclination and then apply that to the apparent length. So just like Dr. TNS taught you, we are going to start with a random line anywhere. Okay, let's make it a thin line, make it a lot easier to distinguish. Okay, what I'm going to do with this line is provide it with the given true inclination, which is 45 degrees. Okay, so sometimes you might need to start from the XY. That hardly ever matters, because as long as the line is at the given angle of 45 degrees, you're more than capable of finishing the problem. So what I'm going to do is just mark a point here that will act as one locus. Okay, so again, a thin line. Next, I'm going to draw an arc using arc by center point from the point of intersection of from here. Just give me a sec. I'm going to trim this off. So I'm going to draw an arc from here onto the 45-degree line with the radius as my true length, which is 50 millimeters, which is going to come somewhere here. This in turn gives me my locus. So the reason I've done that is right now, let's say this particular point is O1 and this particular point is O. So this would work if it were just the true length, but unfortunately, as you are aware, we are not trying to find the true inclination, which we've already been given. What we're trying to do is find the apparent inclination. So I'm going to extend the line for the locus of O. I know that the apparent length is 43.3 millimeters. What I'm going to do is draw a line from O1 in the third stage, give it a length of 43.3 millimeters, and place it on the locus like that. Okay, so this point now becomes my actual O. This becomes my actual axis, which is inclined at a particular value. We know from projection of lines that the apparent angle is always going to be greater than the true angle. Once we've done this, remember, this is basically going to be your axis. So I'm going to mark it as such right from the get-go. Okay. All I've got to do now is pick up the second stage of the object and place it here. So let's do that. Remember, you need everything. Nomenclature, you need dimension, whatever you need. Whatever you used, you need everything to be picked up and placed. So I'm going to pick up the whole thing at the axis alone. And I'm going to move from O1. I'm going to place it here. And I'm going to rotate like so. And place it on the axis. So even though this makes sense in a logical manner, you can clearly see it is paramount that you carry forwards these construction lines, because without these construction lines, it's impossible for you to plot where the actual points in the circumference are. Even here, it is impossible for you to find out where the point C and where the point G is. In order to help you do that, I'm just going to undo a couple of times. I'm going to show you how we can manage that. So remember, we need to plot the point C and plot the point G. So I'm going to use split command again and split this projector at the point G. And that should be more than enough. And I'm also going to split this projector at the point H, so that when I select the points I need, I'm just going to leave away the axis because I've already got it. I'm going to move from O1 to O1 here, then rotate from O1 to the point O over here. Once I do that, it will be clear. It can be clearly seen that all the points in the circumference of the ellipse are visible. So you have A, G, H, F, E, D, C, and P on the circumference. All we need to do now is draw the final front view. Remember, we first have to plot the apparent angle, then move the second stage onto the apparent angle. And whenever you come across any apparent angle, clearly mark what the apparent angle is. Okay, so 45 degrees is a true angle and 55 degrees is our apparent angle. Okay, sometimes you'll get problems where the value or the difference between the true and apparent inclinations are very small. So in those cases, it is imperative that you mark what the apparent inclination is. Okay, so the last stage front view is pretty straightforward. As the procedure describes, I find out whether the base or the apex is closer to the observer. Obviously, the apex is closer to the observer. So in order to complete the final front view, I'm going to first plot all the points. So from O1 to O1 dash, first thing, then from O to O dash. Yeah. Over there, then let's go in a cyclical order. So you have A and A dash. Yeah, some of you might be wondering how one is able to get these dotted lines to help in alignment. That option is basically something called relationship indicator or alignment indicator, which is easily available in your tools menu. Make sure that is on. It's going to save you quite a lot of time in trimming, editing, and marking of the lines. So I've got AB, then I've got C, which is here, then D. Okay, now if these lines are very close together, it's always going to be a problem. So if that is the case, first thing you always have to do is zoom in. So you have D here, very close. So what I'm going to do is I'm going to start from D dash, just draw a line, a horizontal line, mind you, and from there, I draw a perfect vertical line regardless of how long it is. Or what you can do is just draw a line at an angle, at any angle, really doesn't matter, okay, at any length. Then select the line, give it the right value. We know it has to be perpendicular, so 90 degrees up here at the angle, so the line is at 90. Then I keep on using extend until it reaches the point I want it to. Okay, so extend this line up to my horizontal projector, which is there. And once it's there, I trim. The reason I keep on doing this is that at every right angle, you have a point, which makes the business of marking all the base edges a lot easier. Okay, so A, B, C is done. Then I'm going to go to E. Remember, E is the point on which the axis is resting, or rather the solid is resting. So it's going to be the X1 line. Then F. F lies along D. So right there. And then G. G is in the middle along C and O, which is there. Then H close to G, but up here. So it's going to make your life again a bit cumbersome. So what I want you to do is draw any line like that, or a line close to 90 degrees like that. Select it and say it is 90. Oops. So you select the line immediately from H, mark it as 90 degrees from the get-go, and then stop it at the value you need to. Then G, H is done, A is already done. So this gets you all the points, obviously. And once the points are obtained, all you need to do is name them. Okay. So magic time. So I'm back with the nomenclature, as you can clearly see here. So I'm just going to zoom in. So obviously, once the curve is drawn, we need to find out which is visible and which is invisible. So clearly, the apex is closer to the observer when he's looking or she is looking from here. That means I'll have to split the curve into two pieces. So again, I go to split, select the curve, select one endpoint of intersection, which is there, do the same for the other, and you're done. You have one curve like this, which is going to be visible, the other curve like that, which is going to be invisible. So what I'm going to do is mark them such. So invisible portion, then visible portion. And remember, all of them have to be thick lines. So, and you're done. So that is going to be your orthographic projections of a cone such that you have apparent inclination. Okay. So the second portion is pretty much identical to the first. Apart from that, because the question says the top view of the axis makes an angle of 45 degrees, it means that you do not have to mark the apparent inclination. You've been given the apparent inclination. So all that means is you pick it up from here, make sure copy is on, place it there, and then rotate it at 45 degrees. And then obviously you create the final front view, which I'm going to let you guys have a whack at it on your own. So this becomes the difference between part A and part B. Very simple problems, which will fetch you about 30 marks in an exam. This almost completes the problem. The only thing left behind is the axis, which is not such a difficult deal. So select the line type, select the line thickness, draw a line from O1 to O, and you've got the axis. Once you've got the axis, your problem is complete. So this is what you will be expected to do to solve your problems on projections of cones. So as usual, thank you very much for your patience. If you have a doubt, make sure you talk to your class teachers and get them solved as soon as possible. See you next time.